have started the session. Yeah. Yep, we have started the session. I hope my voice is clear. Okay, let me quickly share my screen. And before that, close and okay. Quickly again, this will have to be sorry, okay. Okay. Now I think you can hear me and the slide as well. Let me quickly give you a revamp about what we did in the last session, which you actually missed. So in the last session, I have just given a complete overview of what we did and all. After that, I have explained inverses in detail. What is the meaning of inverses? I know this looks very bad, but in real sense, these things are very simple. So in the previous session, I have explained you in detail what is the actual meaning of inverse. And let me quickly tell you one more time the sentence which I have repeated thousands of times, that let's say you have a matrix and you're doing some operations on it. And this operations can be, this operations can be, let's say you are doing row exchanges or column exchanges or multiplying it with another matrix or anything. Okay. Now what happens is that sometimes matrix will go in a lot of changes, will go in thousands of changes, right? Okay. When the changes might happens, those changes can be two things. One is value type, wise changes. Let's say you have 1, 2, 3, and after the operation you did, it might be 3, 4, 6. Right? It can be that, or else the change might be dimensionality reduction. Let's say you have 3 rows. After doing something, it became 4 rows, right? That might be the another case. So there are two changes, and whatever the changes might be, let's say you have converted matrix from A to B. Okay. Now to go in reverse direction from B to A, we call this path as the inverse of the given matrix. Very simple, easy to understand. Let's not spend much of time here. Now, after that, I have told how, let's say you know how to find the inverse of a given matrix by Gaussian elimination. You just apply Gaussian elimination there, and you quickly extract the inverse of a given matrix. I have explained that. Let's say you have matrix A, you have matrix B, and when you multiply these two matrices, then what will be the resultant? Okay. So what will be the resultant of the inverse of the given matrix? When you multiply two matrices, what will be the inverse of that? I have talked about that. After multiplication, I have gone into a little bit about transposes, right? What is the meaning of transpose? What is the mathematical definition? So this thing you see, right? Aij, HAI. This is the mathematical definition of a transpose. Now, after talking about transpose, I directly went into one question that if you know A transpose, then how can you tell, or how can we find the transpose, the inverse of the given transpose of a matrix? Like for example, let's say I know A and I know A of T, then what will be the inverse of A of T? That was my question, right? So I explained that how we can find all those things in terms of mathematics, right? And finally, after this all proofing thing, we came to a conclusion that A of transpose, the inverse of A of T, will be the transpose of the inverse of A. Okay, that was the thing. After that, we talked about, after talking about transposes, we talked about one of the main topics in linear algebra, which is decomposition of a matrix, right? This is one of the most important concepts, and just let me give you a brief of this in 2 minutes, okay? Now, I want you to imagine that we have a matrix. We have some big matrix, let's say this, okay? This is a big matrix in itself, right? Now, to the meaning of decomposition is that you are breaking the given matrix into 2 segments, right? And breaking of this 2 matrix into 2 segments is known as decomposition of a matrix. And this decomposition is the most fundamental factorization. What is the meaning of fundamental? Quickly come back here. Now, you can see that I have taken an example and all that. And from A to U, the journey, the mathematical relation will be A is equals to LU. Okay. Now I have explained clearly what is the elimination and all that. I'm not going to go into the depths of it, but the thing you need to understand is this diagram where it is. Yeah, this diagram. So, okay, let me just make it really quick because I don't want you to be confused when we talk about future concepts. Okay. Now let's say I have a matrix A. Okay. I have a matrix A and I'm doing some, let's assume that it's a 3 by 3 matrix. It's a 3 by 3 matrix, very simple to understand, everything is clear. Now, when I have 3 by 3 matrix, let's say A, B, C, D, E, F, G, H, I. Okay. Now, what will be the first elimination, right? This will be my pivot and my goal is to make all the elements under the pivot to be 0. Okay. 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 Now, the thing is that when my goal is to make all the pivots elements, all the elements which are present under the pivot to be 0, then can I say that I need to do operation on row 2? I need to do operation on row 3 with row 1 first. Okay, with row 1, I need to perform operations on row 2 and row 3. After doing that, my pivot will be this. Again, I have to eliminate this element. Okay. Now, can I write this operation as A 2 1 and E, sorry, not A, E 2 3 1, right? And I'm multiplying it with A. Okay. I'm taking this E21, E31 are elimination matrices. I hope you remember what are elimination matrices. Okay. Now, the thing is, when it comes to the second pivot, what I'm doing here, I'm eliminating row 3 with row 2 using row 2. So can I write E eliminating second row, third row with second row. So can I write to get U, right? I need to multiply my given matrices E32, E31, E21, multiply with A, and it will give me U. Okay, now if I put this here, then what will happen, like here, I will be having the order will be reversed. There is something called as reversal order or reversal law, which tells that if you want to move matrices, then the inverse will be in reversal order. It means that my order will be E21 inverse, E31 inverse, and E32 inverse. E32 inverse and multiply it with U. Okay. Now, this cluster of elimination matrices is known as L. So what will happen is that my final form will be A is equals to LU. Jabir, okay, tell me one thing. Tell me here that I'm basically multiplying everything and I'm getting U. Why are you putting this left-hand side to right-hand side? And why do we do that in the first place? I want you, everyone of you who's listening or who's present here, to try with one example. Take a matrix here and find its elimination matrix because we already know U, right? You know U, you know A, and find all this E21, E31, E32. Now multiply it on the left-hand side and try multiply it with its inverses. You will find out that the multiplication process of finding the inverse is much easier. Like the multiplication of inverses are much easier, and it exactly tells you that what are the things you're doing. Like if you see here, I have taken an example and multiplied it here, but you can see exactly that I have to remove 2 in row 2 using row 1. Here, I'm exactly writing that I need to remove 5 times, 5 times with row 2, right? Here I have 1, right? So that is the thing. The thing is that this form, let me tell you in very simple words that A is equals to LU is A is the complex matrix which has a lot of values, and L is like the blueprint of the elimination you did. Blueprint of elimination. It exactly tells you by just looking at L, you will know that what are the operations you have to perform to get this upper triangular matrix, to get this simplest form of matrix. Okay, like you can imagine that you have a house, right? You have a house or you are baking, right? You want to make a cake, right? This cake is a very complex thing, right? This cake has sweets, baking powder, eggs, all this and different of ingredients it contains. It's a complex object in itself. Similarly, the matrix here has hundreds of values, hundreds of dimensions. It's a complex thing, right? But that complex thing can be broken down into two parts. Like making cake can be broken down into two parts. First, you need to know the recipe, right? You will follow a recipe book. After that, second, you need ingredients. Ingredients are the fundamental parts. Okay, are you getting me? Now, the thing is that, let me come here, right? So, to what I'm doing is that instead of thinking how I got this big house, I'm thinking in terms of reverse order. First, I will have a blueprint. Then it is given that to build house, first I need cement, sand, bricks. So what I'm doing is that I'm combining the mixture of blueprint and this fundamental elements to get the complex thing, which is my house, which is my resultant matrix. So you can imagine this as well. You're breaking, let's say you want to break the matrix into its fundamental parts, then that fundamental part is A is equals to LU. Okay. Now, after talking about A is equals to LU, again I came back to transposes. I have explained some rules of transposes that you have studied this hundreds of times in your school times. That if you have a matrix AB, if you transpose that, then you will get B transpose and A transpose. Right? That is first rule. And second rule is that, like, this is the second rule, right? If you have A, if you have AT, then the inverse of AT will be the inverse of A transpose will be equals to A inverse transpose. That is a little bit tricky to speak, right? But by just looking at the equation, you will know. And after that, I have talked about one important concept, which I have just touched on top, which is symmetric matrices. The definition of symmetric matrix is that when A and AT becomes equal, right? Those type of matrices, those sort of matrices, we call them as symmetric matrices, right? Even though you swap rows into columns, columns into rows, you'll get the resultant same matrix, right? That like matrix is a very important matrix when it comes to applied mathematics, because we will be talking about a new concept, very near, which is orthogonality of a matrix, right? Perpendicular, how you can tell a given matrix is perpendicular to another, right? So in that, they will be helpful. After that, in machine learning, symmetric matrices are going to be really important, right? When we study algorithms, we'll see how important they are. But let's talk about how can we build a symmetric matrices. So to build a symmetric matrix, the recipe, the rules are, first take a rectangular matrix. That rectangular matrix can be a square matrix. It doesn't matter. And take its transpose, multiply them, both of them, and what the result you will get is a symmetric matrix. The result will always be a symmetric matrix. So this is a quick recap of the last session. Now let me come back to our Blackman. And in this session, we are going to talk about one of the most important topics of linear algebra. And let me write it here, which is very small because I don't have much space. Vector spaces. Let's talk about what are vector spaces. And like from now on, lecture has started. I was just giving you a recap and all, but I want you guys to pay full attention, because when I was studying this, I tackled thousands of doubts, right? Because this is more of a theoretical concept than a practical thing, right? And this is really important for our upcoming sessions. So pay full attention. Okay, let's talk about what is a vector space. We have vectors, right? We have n-dimensional vectors. What do I mean by vector? Right? Let's talk about vectors first, right? So a vector, what is a vector? A vector, if you see the definition in terms of physics, you will say that a vector will have a direction and a magnitude, and it should be closed. It means that it will have a starting point and it will have an ending point, right? But in mathematics, right, that definition is 100% correct, and you can apply that definition here as well. But in mathematics, we try to describe a set of points with a straight arrow, right? And we call this thing as a vector. For example, if I'm writing a matrix A is equals to 1, 2, and 3, 4, right? So it has two column vectors. 1, 2 is a vector and 3, 4 is a vector. And how I can see this two vectors, vector 1, vector 2, let's say I have x-axis and y-axis, okay? Now 1, 2, right? So x-axis will be 1 and y-axis will be 2. The intersecting point, this will represent a vector. Okay, this line from origin to that point is known as a vector. Similarly, you can draw like 3, 4, 3, 4. So it will be the same vector, but with a larger magnitude. That's it. Okay, so this is the definition of vector. This is how we imagine vectors. Now, what is a vector space? I want you to imagine that I have n number of vectors in a given dimension, right? I might have one dimension, I might have two dimensions, I might have three dimensions, n number of dimensions, right? Okay. Now, a vector space is basically a space where I have n number of vectors. Okay. And this, a given set of vectors or a given set of space, you will call that space as a vector space if they follow a set of rules. I will talk about what are these rules and all, but the definition of vector space is an environment. A vector space is an environment where there are a bunch of vectors, and these vectors can be 10, these vectors can be 20, these vectors can be infinite vectors in a given space, right? They can be any number of bunch of vectors, right? Any number of vectors, like an environment where they are bunch of vectors, and these vectors are following some rules. Okay, so this is the given. What is this environment? Right? This environment is basically space. I don't know why my computer screen came here. Okay, anyways. So the point I was telling you that here is that in a given room, basically a room is a space, right? I can have, like, I want you to imagine vector, imagine origin. I have a vector from here to there, here to there. A vector can be parallel to x-axis, a vector can be parallel to axis, anything, right? The thing is that all these vectors in this space, I call them as vector spaces, if they are following some rules. What are these rules? The rules are that, let me write it here. The rules are this. First, if you have a vector P and vector W, okay, I'm taking two vectors for example, right? And these rules have to follow like by each and every vector in the given space, right? It is mandatory. If some vector is not following these rules, then it is not a part of vector space. Okay, although there'll be like nothing which is not a part of vector space. Okay, let's not go into that, but let's come to rules here. I have vector V and W. Okay, now what are these rules? The rules is that when you have V and W in a given n-dimensional space, let's say this space is R2. For example, I'm taking R2. When I write R2, a real number, two-dimensional space, right? So all the numbers are real numbers. If they are like imaginary numbers, then there is a probability that vector spaces, the given vectors is not a part of space. But for simplicity, I'm just taking all vectors are real number based vectors. Okay, so let's say I'm having a vector, let's say in a given R2 space, I'm taking an example such that you will understand. In a given R2 space, my vectors can be 0, 0 can be a vector. After that, 1, 2 can be a vector, right? Similarly, in book, Hilberstein book, you will find this example, right? Pi, e can be a vector. So all this you can see, they are having two units, right? And all these vectors belongs to R2, right? Now, the first rule says that, let me write it here, right? Remove this and let me write the first rule. The first rule says that if you have a vector V and W, then the sum of this vector, W plus V or V plus W, should belongs to R2. You're taking R2 as an example. Okay. Similarly, if you're having V comma W and if you're multiplying it with a scalar, let's say C multiplied by V or D multiplied by W, irrespective of what you're multiplying, like you can take any scalar and multiply it with a vector. A scalar is basically a number. You're taking a vector and multiplying it by 2. Here 2 is a scalar, right? So you're multiplying with a scalar and the resultant should always be in R2. That is the thing. If it is following these two things, then the given vector space is known as, then the given set of vectors is a part of the vector space. If some vectors are not following this, then they are not part of my vector space. I hope you have understood what is the meaning of vector space. Okay. Okay. So this is the thing. Like you can add them and they will remain in the same dimension. You can multiply it with a scalar and they will remain in the same dimension. Okay, and I can show you the representation of this given example, right? I might have, let's say this is my xy and have 0, 0. So this is one vector, which is origin itself, right? And I can take 1, 2, right? This is 1, this can be 2, right? So this will be here somewhere here. So I can draw this vector. So this will be my vector. This is my vector 1. This is my vector 2, which is 0, 0. This is my 1, 2. Okay, similarly, you can take pi e. E is like, what is the value of e? Let me search quickly. What is the value of pi and e? Pi and e. So E value is 2.7 and 3.14. So can I take like pi and E, right? So 3 will be somewhere here and 2.14 will be somewhere here. So the vector which we will get will be somewhere here. So this will be my vector 3, which is pi E. So the collection, right? You can see that this vector 1, 2, 3. So all these vectors, like whatever the vectors you have, which is coming in R2, is a part of the vector space. I hope you are clear. What is the meaning of vector space? I can give you like one more example, a real-time example actually. Let's not talk about theory. Let's talk about a real-time example. Okay. I hope you might have played games, right? You might have played Free Fire, PUBG, or Minecraft, or GTA, right? GTA is a perfect example. You have a map, okay? And you can move in the map, you can fight in the map, you can jump on the map, you can do whatever you want. But what will eventually happen is that you will remain the part of that given dimension, right? If it is a snake and ladder game, then you can move anywhere. You can add a vector with itself. You can multiply a vector, right? The snake size will move, but it can move in XY direction only, and it will remain the part of XY. No matter how much you add two vectors, how much you multiply two vectors, it doesn't matter, right? It will be a part of that vector space. It will be the part of that dimension. If it is a snake and ladder game, R2 dimension. If it is a GTA or PUBG or Minecraft, it will be in R3 dimension only. Okay, so that is the meaning of vector space. Okay, got it. I can take another example that this is example one, which is second dimension vector. I can take R3 as well. Let's say 3, 2, 0, right? In this, I can take X, let me draw correctly, X, Y, and Z. Okay, now 3, 2, and 0. So 0. The vector which I get on result, right? The intersection of this point somewhere here. And this is a vector, three-dimensional vector 3, 2, 0. You can multiply this vector with, let's say, 2 times. That will get enlarged by 2 times. You can like multiply it with a negative number. It will go backwards. You can add with, let's say, -3, -2, 0. The vector will remain here. You can add it with another number, right? The vector can orient somewhere. Let's say I'm adding with 3, 2, 1. Then the direction of the vector may rotate, but it will remain within the R3 space. Okay, now let's talk about another topic. Let me change the pen ink. The topic name is subspace. Okay, I want you guys to give me a thumbs up if you understood what is a vector space first. Give a thumbs up, then we can move to next topic. Okay, now let's take, let's to explain the meaning of a vector space. Like, okay, let me tell you a real world example. We are mathematicians, right? We are mathematicians and we are scientists, right? And we know, like, for example, let's say you want to test a atomic bomb, right? You can't directly go and blast on people just to test it. You will create a small environment, a portion of space, and in that space, you test various things. Similarly, if you take this entire universe is like a very large space, and it can have millions of vectors, right? If you take GTA game, GTA is a very big map, right? It's like now in GTA, imagine that you're just taking one small portion, right? You're creating one small portion and you're doing all the experiments on that mini space. And that thing, right, in the given entire given space, let me draw correctly. Uh, in the given entire space, this is our entire R2 space. You are taking some portions, right? Can I have a pen? Can I have a? I need a marker something, right? Can I have a marker? I think I can have a marker, but I don't know exactly how we can use it. Okay, anyways, I'll just draw here that, okay, with different pen would be good. Yeah. Okay. Now, imagine that I'm taking this space. Let me draw perfectly. Yeah, I'm taking this space. Okay. Now, R2 space is this, but I can't take entirely. What I'm doing is that I'm taking small portion, okay? And whatever the vectors in this, I'm taking them and I'm doing various things with them. So this thing, this small thing, whatever the vectors which lies in this mini space, they are known as the vectors of the given subspace, and this small portion is known as the subspace of the given vector. Okay, understood? I hope you have understood. Now, there are certain things you need to understand about a vector. Okay, so specifically talking about like when can be a vector, when can be a vector part of the given subspace, right? Part of the subspace. right? Which vectors are the part of the subspace, and how you can tell. So I have taken an example, like, okay, let me tell you this. Like, how can you tell that this given portion is a subspace or not? Okay, so for that, there are 3, 4 rules. Like, let me write it here. First, is that the given subspace, right? Let me like correctly write the question, right? So when can you tell? When can you tell that a given vector or a given space is a part of the? When can you tell that a given vector is a part of the subspace? If it follows two things, right? Can be when can a vector part of this subspace and when it can't? Okay, let's talk first when it can't. Okay, now just imagine that this is my xy plane, because we are talking about second dimension, and this is my vector. You might say, Jabir, this is lying in this portion. So this given vector is a part of the subspace, right? The answer is no, because the rule says me that if you add v plus w, it should be the part of the given space. Okay, it is, let's say this is my space, right? Now, let me draw it with a different thing. Let me draw with a different thing for differentiation. This is my vector. Okay, this is my given space. Let's say the space name is R. Okay, now if you are adding, let's say, a vector, this is my vector V, for example, and I'm adding plus W. So it is going upwards. Okay, I'm adding W. So you can see that the vector I'm getting, the resultant vector is still a part of the given space R. Okay, first rule is satisfying. Satisfying. Now, what about the second rule? Let's say I'm multiplying this vector V with minus C, right? I'm multiplying with the minus C. What will happen is that if the C is big enough, right? For example, uh, let's say this is my xy plane and the length is something 2, and I'm multiplying it with minus 3. So what happens is that the vector will rotate and go back with minus 1, because minus 3 plus 2 will give you 1. So it will go backward direction. So the resultant of the given vector would be this, and the length would be minus 1. Are you getting me that? If you see, if I'm multiplying the given vector with a scalar, it is going out of the given space R. Okay, if it is breaking any of these two rules, then the given vector is not a part of the subspace. I hope you have understood that. I want you to imagine this. Like, there is a room, right? I have my room in front of me. Now, I have fixated that this is my vector space. Whatever I'm seeing, this 4 corners room is my vector space, and all the vectors should lie here. Now, imagine that the vector is coming from the bottom of the ground to up, like there, like okay. This is my room. Let me. I don't want to confuse and talk much, but okay. This is my room. Okay. Now, this is my room, right? Now, imagine that my vector is going from here to all the way opposite of the room. Okay. Now just imagine that this is my vector space. This is my vector space. I have imagined this. Okay, this is my universe. Okay. Now whatever happens, right? Whatever operations I'll do, the vector should remain inside my vector space. Now just imagine that the magnitude is x. Now directly I have multiplied it with minus 2x. Then the vector will immediately go out of the room. So if this condition happened, then the given vector is not a part of the vector space. This can be a vector space. This can be a vector space. Are you getting me? Right? The thing is, if the given vector is going out of the provided space or assumed space, then it is not a part of the that particular space. Okay, understood. Now, there are some rules which a subspace has to follow, right? And what are these rules? The first rule is subspace rules of subspace. Let me write it here. The rules of subspace. Okay. The first rule is if you take, before we move into this, if let's assume, right, I'm taking a R2 space, then the subspace of the given R2 would be all the R2 itself, right? For given R2, the entire R2 is a subspace, right, for itself. Now, the second is that any line passing through 0, 0. Okay, so all the lines which are passing through 0, 0 is a part of the subspace for R2. Okay, they are subspaces for R2. Now, after that, a point, basically origin. So these are the different scenarios of subspaces that can be possible for R2. If you take R3, if I talk about R3 specifically, for R3, what are the possible subspaces? First is all the R3, right? Or the R3 entire itself will be a subspace. Second is that a lane passing through 0, 0, 0, right? And a line passing through 0, 0, and the third point would be origin itself, right? Let me tell you very clearly that subspaces has to have origin, because the rule, if just imagine, okay? Let me ask you this question. I have my two-dimensional space. Now, can I tell this particular part as a subspace? Tell me. Will it be a subspace or will it not be a subspace?
It might be.
It is not a given. It is a subspace, but it is not a subspace of a vectors. Because just imagine that, okay, I have a vector, or let's say my vector is something like 0, 0, 10. Okay. And what is the given definition of a vector? Tell me. Sorry, what is the given definition of a vector space? The given definition are, if you add a given vector with a vector, it should remain in the same vector space. If you multiply it with another scalar, it should remain in the same vector space, correct? Okay. Now, the thing is, let's say I'm multiplying with 0. Then immediately the vector will be here, not here. But my vector space lies here. So what is this contradiction? What is the meaning of here? What is the meaning of this? Right? Because this thing is contradicting. That is why every subspace has to pass through origin. Because if you multiply it with 0, it will come at origin. And if your vector lies here, and if you are multiplying it with 0, then it will come outside of the given vector space, and it will break the rules which you have defined here. That is why a given subspace has to pass through origin. Okay, so I hope you have understood what is the meaning of a vector space, what is the meaning of a subspace. and what can be the subspace of a given dimension. Okay, so I want you to tell me, first of all, what is a vector space? Go ahead.
Vector space is a space where a group of vectors are present and which follows rules.
Correct, correct. And what are the rules they have to follow? This vectors has to follow.
If we multiply a vector with a scalar, then it should remain in the same space. And if we add two vectors or multiple vectors, it should remain in the same space.
Got it. Now, what is a subspace?
Subspace is a part of a vector space.
Okay. And what are the subspaces of vector space R3?
R3 itself,
Okay.
a subs
So entire R3
R3
is a subspace itself. You can imagine that. Second,
are planes which are passing through 0, 0, 0 origin. And next is the origin. Origin itself is a part of sub.
uh, so like a plane has to pass through, a line has to pass through, and origin, the point itself, right? So can I say that I have xy, or I have three-dimensional space? Let me write it here. I have this three-dimensional space, x, y, and z, and this particular portion I'm taking. Okay, can this be a part? Can this be a subspace of the given vector space R3?
It
Yes
cannot be a
or no?
no.
Why no? Why yes?
No, because like as you said, if we multiply with a scalar of quantity 0, then it will go to origin, and the origin is not a part of the given subspace.
Exactly. Exactly. Right? It will go to origin. Right? They are all vectors will go to origin. Right? Let's say you have all like thousands of vectors here. Right? You have thousands of vectors here. Now, just imagine that you're multiplying with a scalar 0. It will directly go to a point which is not in the subspace. That is why every subspace has to pass through origin. If something is not going through origin, then it's not a subspace. It's just a random space in the three-dimensional R3, right? In the R3 dimension. Very clear. Now, this is related to physics concept. Like in physics also the same concepts apply. In linear algebra also the same concepts apply. Now, when it comes to matrices, we are talking about matrices, right? Okay, I will change the pending now. This is the third topic. We have talked about vector space, we have talked about subspace. Now we are talking about something called as column space. And this topic is my favorite topic, and this is going to be the most important thing in the next concepts. So I want you to have open ears, and if you have any doubt, raise your hands right away. Okay. Now imagine that I have a vector. Let's say I have 1, 2, 4, and what example I have? 3, 3, 1. Okay. So 3, 3, 1. Now, can you tell me which dimensions this matrix has?
3 dimensional,
3 dimensions. And how many vectors do I have?
two vectors.
2 vectors. So let me just quickly draw it. Let me just quickly draw it diagrammatically. I will use this diagram only. So 1, my 1, x is 1, x, y, z. Okay, x is 1, y is 2, and z is 4. So somewhere my vector is, let's say, here. Okay. So let me draw a straight line. This is my vector 1, or let's say column 1. This is my first column vector. This is my second column vector. Okay, I will draw the second vector now with a, let's say, different pen. Okay, 3, 3, right? So x is 3, y is 3, and z is 1. So let's say this vector is somewhere here, C2. Okay, now I want you to listen to this very carefully. The linear, let me go back to blueprint pen only, because there will be another topic for which I'll use this pen. So composing blue pen. You can write these equations as well, that the linear combinations of column vectors, okay, all the, right, let me just remove this, all the linear combinations of column vectors, right, all the column vectors are, all the column vectors are known as column space. This is the definition. Okay. Okay. Diagrammatically, I'll show right now that this is my C1, this is my C2, and all the things which are coming in between C1 and C2, whatever the vectors, this vector, that vector, this vector, whatever the solutions, right? All this is known, all this space which you are getting here. Okay, this space is known as column space. I hope you have understood. I hope you have understood the meaning. Okay. This is the meaning, and I can talk about like column vectors in detail. But before that, um, I want to talk about subspaces a little bit more. Okay, so let's go to subspaces, right? I hope you have understood the definition of column vector. You have two vectors, right? Let's say I have like ax is equals to, this is a, right? So a x is equals to b. Now, whatever the linear combinations which you get for all b's, whatever like linear combination of x, right now I have two unknowns, right? So x1 and x2, two dimensions, right? So two unknowns. Now, for all b's, like I might have matrix b1, I might have matrix b2, I might have matrix b3, whatever the matrices might be. For all b's, whatever the x1, x2, x3, x4, like whatever the solutions I get, these solutions are known as my column space. This is mathematical definition. This is English definition. This is geometric definition. I have given you all three definitions. I hope you will be clear. Now let's go back to matrices and try to insert sets here. Okay, so I hope you have understood that a subspace has to follow these things, like it should pass through its like lower dimensions origin. It should, like, let's say if I'm talking about R2, then R2 itself is a subspace and it should pass through origin and blah 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 and all those things. And at most it has to follow this thing. Like if V and W are two vectors, then V plus W should lie in the given subspace. And C cross C multiplied by V plus W should also lie in the subspace. Okay. Now imagine I'm taking this diagram. Okay. I'll show you one thing. Very interesting thing, right? I have written this in my book as well. The concept is that, let's say I have three-dimensional space, okay? This is going to be really interesting. Origin y x z. I have taken a three-dimensional space. Now, let's say I have a plane. If this is my, like, imagine that I have a wall here. If x is like my plane is something like that, I'm writing a plane. A plane is something like this. This is my x. So a plane P, and a line is not on plane, but it is like clearing one point of plane. Okay, plane. And both are passing through origin. Let me just try that line. Now tell me that will P intersection, before going to intersection, P union L, whatever I get, right, whatever the answer I'll get, right, will this be a subspace or not? Yes or no? If yes, why yes? If not, no, why no? Tell me. Like, have two things. One is a plane, right? A plane like this, and a line is going like this. Okay. Now I have taken union of both. Okay. Now tell me what will be like if I take P union L, the resultant I will get of this two will give me subspace or not. Really interesting question. If you see here, what I did is that I have taken my concept of subspace as basically vector spaces and integrated it with sets. So go on, tell me. Will it be a subspace or not? How can we tell? I can tell if this whatever the vector I take, right? Whatever the vector I take in their paths, if those vectors are following these two things, then yes, P union L will be a subspace. If no, if they're not following, then they are not. Simple, easy to understand. But how you can tell? How you can tell? Like, let's say this is my P, right? Let me draw with. Why don't I have like multiple pens? Okay, I do have multiple pens. Okay, I didn't know that. I just have to click yes. Okay. Okay. So let's say this is my P, right? Or this PPP. Now this is my L. Now you can see that this is a. I hope you guys are not sleeping. Maybe you're sleeping, but this is important. Now you can say that this is my vector V1 and this particular thing. Exactly. This particular thing is VD. Now, what will happen if you add V1 and V2? V1 plus V1 plus V2. Tell me what will happen. I will get a resultant vector, something like this. Let's say V resultant. Now tell me, like this is my plane, this is my line, and I'm getting a vector, something like that. Right? Now tell me whether this VR, which I got, is a part of this union. Right? Tell me.
Yeah.
No. See exactly. Right? This is like, okay, let me draw this. This and this should be my answer, but I'm going totally out. You need to visualize this. Okay. Okay. Let me remove everything. Now, see the diagram. See the diagram very clearly. We have L. We have P. Okay. Okay. We have L. We have P. And I have vector V1. I have vector V2. Now, the definition is that if I'm adding another vector with vector V1, it should be the part of P. If I'm adding something, some another vector with V2, it should be the part of L. But what is happening? It is going out. They are not even following the parental spaces. Because of this, it is not a subspace. So if you union two given spaces, then the resultant you get most of the times it is not a part of the subspace. Now, what about intersection? What about intersection? Right? Tell me what is the common point. The common point is origin. Okay. So origin. Is origin, if it is a origin, then will this origin be a subspace or not? Will its origin is a subspace or is it not? Tell me.
It is.
It is. Correct. It is a part of the subspace. So union, in most of the cases, they will not give you a subspace, and intersection will give you subspace. Okay, so this is a concept related to sets as well. Now let's go back to our column spaces. Okay, now let me take an example, and with this example, I can tell you, I can explain you in detail. Okay, what are column spaces and all. Let's say I have a column space A, column a vector with column spaces 1, 2, 3, 4, 1, 1, 1, 1, and 2, 3, 4, 5. Okay. Now, what is a column space? Column space is all the linear combinations of the given columns. Given columns. So now tell me, like, how many dimensions are there?
4 dimensions.
4 dimensions. So the spaces are 4. How many unknowns are there?
3 unknowns.
3. 3 unknowns are there. Okay. And what will be the resultant? B. How many dimensions the B will be? 4.
4 dimensions.
The dimensions of B will be 4. Okay. So if I write it diagrammatically, then like we can't visualize this because this is a 4 dimension. We are someone who live in 3 dimensions. So it is impossible to imagine a 4-dimensional vector for humans at least. Okay. So I will just draw like in terms of matrices, in terms of linear algebra, right? 1, 2, 3, 4. 1, 1, 1, 1, and 2, 3, 4, 5. Okay, and I'm multiplying with 3 and x1, x2, x3, and I'll get 4 and p1, p2, p3, p4. Okay. Okay. Now my question is, what can be the solution? What can be my column space? Right? And. Uh, the question is, let me write a question. Let me write. This is interesting, very interesting question. Okay. So let me write it. Does, right? This is ax is equals to b. If you remember, this form is ax is equals to b, which we studied in lecture 1. Okay. Now my question is, does the equation a, does the equation a x is equals to b has a solution every time, has a solution for every b? Question mark question. Tell me. Right? Let's say I'm putting some random numbers here. if I put any random number in R4, will I have the solutions? So to answer this, we need to think logically, right? What is this? What is the given thing? The given thing is basically linear equations with 3 unknowns but 4 equations. Right? Are you understanding me? Right? I have 4 rows, right? So I'll have 4 equations, but the given are XYZ only, right? 3 unknowns. Okay. Now tell me, I hope you have understood, I hope you have learned in school 8th, 9th, 10th, somewhere in our classes that for a system of equations, do you think, or let me rephrase this question correctly, right? I'm giving you a system of equations, and do you think that those system of equations will always have a solution?
No.
No, you won't have. So if I put any ABC here, will I get a solution?
No.
No, right? That is the thing, right? If you put anything, any value as P1, P2, P3, P1, P2, P3, and P4, if you put any value, and if you are getting all the solutions, for any value V1, V2, V3, you know what will happen? The given, right? The solution of X1, X3 will be R4 itself, right? From our logical standpoint, we are clear that this will never happen because there are only few numbers which you can put to get answer, right? If you put anything, you will not get answer. Okay, so my column space is a small part of R4, but not entire R4. This is the point I was trying to make. Okay, so you can't put any value. Okay, now tell me what piece I can put. So we have understood that only there are certain pieces. What are these? Please tell me. Okay, it is hard to like directly tell answer, but can I write my B1, B2 as B1, B2, B3, 4 as 1, 2, 3, 4, right? If I take B1, B2, B3, I'm just taking an example, right? What will happen to a matrix? This is my matrix 1, 3, 4, 1, 1, 1, 2, 3, 4, 5. Okay, and x1, x2, x3, x1, x2, x3, right? Is equals to, I'm just taking a random example, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, 4 numbers. Now, can I write x1 is equals to 1, x2 is equals to 0, x3 is equals to 0? Okay. Now, can I write b1, b2, b3 as 1, 1, 1, right? And if these are 1, 1, 1, then don't you think my x1 will be 0, x2 will be 1, and x3 will be 0? Right? Now, if I write b1, b2, b3, b4 as 2, 3, 4, 5, okay, then my x1 will be 0, x2 will be 0, and x3 will be 1. Okay, so what I'm trying to tell you is that even though the given dimensions are 4, but the column space is a plane, right? For this example, the column space is a R3 plane, because see this too, browser quota existed, changes will not be saved. Oh God, what is this? I don't understand. Can you hear me?
I can hear you.
Okay, okay. Let's make it really quick because I don't know what is this. What is this? Oh, acha, acha, acha. So it is showing me that whiteboard is existed. You wrote too much. But anyways, let it believe it. It's not Teams. Now, the thing is, let's come back to topic. I have four, in my example, I have 4 dimensions and 3 unknowns. And these 3 unknowns are 3-dimensional column space. Now, if you observe column 1 and column 2, right? Column 2 is nothing but column 1 plus 1. Hmm? Is it or is it not?
Yeah, it is.
It is. So what I'm doing is that I'm taking one vector, I'm adding +1 to it, and I'm getting column another like column 3 vector, right? So basically, what I'm trying to tell is the answer I will get, right? The column space I will get is a plane, is a 3-dimensional plane, right? That is the thing. That is the thing, right? So I hope you have understood what is a column space and how we visualize it. And I did an example in front of you, right? And you can draw this diagram, and whatever the diagram you get, it will be something like that. Like column space will be something like that. It will parallel to one of the things. Like column 1 will be parallel to column 3. It means that x1 and x3 will be correlated with 1 or 2. That's it, right? You just have to add 1 or -1, you will get x1, x2, something like that. Okay. So that is the thing I was trying to tell. I hope you have understood column space. Now let's talk about the last topic, which is null space. Null space is a special condition that, okay, here, take this example. In this example, uh, the solutions can be, I wrote like 1, 0, 0, 0, 1, 0, and 0, 0, 1, and whatever. Like I might have infinite solutions, and combining all these vectors is my column space. Okay. Now, here Ax is equals to B, and I can have X as infinite vectors and B as n vectors, right? Or else, if I have n solutions, then B can be n. Okay, are you getting me? Right? If B is something, let's say if B is this, then I'll get this solution. If B is this, then I'll get this solution like this. If there are n number of B's, then my solutions would be n. Right or wrong?
Yeah.
Okay. Now, let's assume that if I'm taking a condition where B is 0, 0, 0, 0, then my equation would be, I'm taking one B, right? Then my equation would be A x is equals to B. And if I specify it, then Ax is equals to 0. And all the x's which I get for this given equation, all the x's, or I can say linear combinations I get for Ax is equals to 0, that is known, those all vectors, those combination of all vectors is known as null space. Okay, so we have talked about very messy board, but we have talked about 4 different things: vector space, subspace, right? Subspaces of R2, subspaces of R3, conditions of a subspace and vector space and all that. And after that, column space, null space. Very easy to understand, very easy concepts honestly, right? You just need a little bit of visualization and all. Now in next lecture, we will talk about ranks. We will talk about, like now, we will not touch elimination from now on. We'll mostly focus on uh, column spaces. Every time you will hear hundreds of times column spaces. So this is pretty much it. Thank you for watching. Thank you for listening. It really means to me a lot. I'll see you in the next one.